morning. What we will do today is we will discuss exclusively the properties of least squares estimator, and then if time permits we will look at weighted least squares as well. So, what we discussed yesterday is of course the solution to the OLS problem and also the goodness of fit measures, mainly the R square and adjusted R square. The R square tells us how good a fit the model has obtained with the help of least squares. You see, the model by itself cannot really understand the data. You need an estimator which essentially trains the model to understand the data. And now we are at the moment we are talking about the least squares estimator. An R square measure and adjusted R square measure tell us how good the how well the model has understood the data, and the difference between R square and adjusted R square is the penalty term that is kind of included implicitly into the or explicitly I should say in the adjusted R square, whereas in the R square measure you can achieve high R square measures with over parameterized models, and R square would not tell you that it is happening. So, let me actually quickly show you an example in R where let me here. Alright. So, here we are just going to work with a synthetic example where it is a very simple example. We consider some series y which is being constructed as some a naught plus a1 t plus a2 t square. In fact, let me say k here, it's k square, and what we will do is we will generate the time vector first. So, I am going to do this and let us say call this as k vec, and then let us generate yk. So, I have just arbitrarily chosen the values of a naught, a1 and a2. Of course, it is a quadratic. Let us assume that we do not have yk, but rather measurements of yk, where we add some noise to yk. As you can see, the second term represents the, you can think of it as measurement error or whatever cannot be explained by your quadratic polynomial. You could adjust this factor here 0.2 to any value that you want, but remember that as you are increasing that factor you are raising the levels of noise and lowering the signal to noise ratio, and therefore, as you increase the levels of noise you should expect poorer and poorer fits because our regressors are going to be 1 k and k square. Those are the regressors that we are going to use. Yes. Yeah, I will change. Oh, sorry. Yeah, earlier I had t vec. Thank you. All right. So, let us generate here, we will just arbitrarily choose 0.2 or even 0.3, and it is a good idea always to plot the obtained measurements as a function of the time, and as you can see here, maybe it is better to plot a line type plot. So, as you can see here there is a trend, right. Let me zoom this out for you, zoom this in, and then so you can see that there is a trend here, there is a quadratic trend which is what we want the model to capture, but there are also local variations. Now, underfitting happens when we miss out this quadratic trend, maybe we fit a straight line. Overfitting occurs when we start modeling the local variations which are essentially due to noise, and that is what I always say when you are working out an assignment problem. There is a concept involved underneath every problem, and there are numbers specific to that assignment to that problem. If you understand the concept, then well and good, you have gotten, the purpose is served, but if you try to now start memorizing the numbers, then that essentially is overfitting. So, let us actually assume that I know it is a quadratic, visual inspection, and then fit a model, and as I have already shown you once how to fit linear models using least squares. The routine is LM. So, let us say here we say lin mod yk is LM we use the measurement, and then we pass on the regressors in this fashion. Remember, you have to tell LM that there are these at least three regressors, but the third regressor need not be mentioned, which is 1, that is there by default as an intercept term. So, we have to supply the other 2 regressors, and that is it. So, you would be making a mistake if you simply supply k vec square plus k vec, because then it will club those 2 and think of that as a single regressor, all right. Now, it is time to pull up the summary on this. So, when you do this, the summary brings out a lot of interesting pieces of information relevant to your model. First, it gives you the estimate, essentially your A0 hat, A1 hat and A2 hat in the first column, and then it also calculates a standard error. So, today I will talk about the theoretical expression that allows us to calculate this standard error. Remember, we have what kind of noise have we added here? Colored or white? We have added white noise. So, when we go to theory, we will see that results are obtained only for white noise, generally available for white noise type of errors. When it comes to colored errors, what happens is also said in the theory, but we do not have an expression for computing the standard errors, because we will see that least squares estimates are efficient only when the errors are white. In other words, it gives you minimal variance estimates when the errors are white. So, first let us go through this quickly and then go back to the theoretical expression. We will also talk about bias a bit shortly. So, here you have the estimates and the standard errors. Remember, as I said, always in any model estimation exercise you have a hypothesis test underneath, and that hypothesis test is concerned with essentially the parameters being 0 valued or not. Whenever you have a hypothesis test of this form, whether it is multiple parameters or a single parameter, this is not only called a hypothesis test, but also known as a significance test. Because what you are asking is if the parameter estimate that has been obtained is significant. Even if the truth was that theta is 0, you would obtain some non-zero value of theta, right, that we already know. So, the question is whether the obtained value of the estimate is significant. The moment you hear the word significant, you should think of this hypothesis test. So, here we are asking if A0 is 0, A1 is 0, A2 is 0, we are conducting such kinds of tests. Either you can look at the standard errors and construct the confidence regions, but what is required for constructing the confidence regions? The distributions of the estimates. Again, theory will tell us very soon what is the distribution of the parameter estimates obtained using the least squares method, and it turns out that fortunately it is just a Gaussian distribution. So, here for example, if I want to construct the 95% confidence interval, I can take the estimate obtained plus or minus, if it is 95%, roughly twice this standard error, right. 1.96 times sigma theta hat is what you want to add. This is sigma theta hat that you have, and quickly you can check if 0 is contained in the confidence region, because what we are testing for in the hypothesis is if the postulated value is 0, and remember there are 3 different ways of checking the performing the hypothesis test, of which we are talking of the confidence interval approach. So, if I construct the confidence interval here, what do you think for any parameter that is being estimated here, would the confidence region contain a 0, 95% confidence interval? No. So, which means that essentially we reject the null hypothesis that A0 is 0, A1 is 0, A2 and 0 individually. So, all of them are significant. That means I have to include those regressors in my model. Very soon we will over parameterize, that is we may fit for example a 4th order polynomial instead of a quadratic, and see if my significance test tells me that I should have excluded those regressors. Anyway, so you can also look at the p value as I have mentioned this before long ago when we were discussing non-stationary models and removing linear fits. At that time I had pointed out as well that you can look at the p value. If the p value is low, then the null hypothesis must go, right. Low meaning low compared to your significance level. If you set your significance level to 0.05, then all the p values are lower than that, which means a null hypothesis is rejected. So, again a different way of conducting your significance test here. And the stars are telling you that they have already done that for you. So, the 3 stars would mean that these are like the star coefficients for you, they have, you can't really exclude them. The t value that is being reported here is the t statistic. Remember, there is a third way of conducting hypothesis test, which is based on the critical value approach. You compute the statistic and compare it with the critical value. The statistic is being reported here. What is missing here is a critical value. You can generate those critical values in R by turning to Qt. In this case, although I said earlier that theta hat follows a Gaussian distribution, when the variance of the corrupting noise is unknown, theta hat follows a t distribution. We have talked about this in the context of sample mean, right. When we were conducting hypothesis test on sample mean, we had 2 situations, variance unknown and variance known. When the variance is known, sample mean follows a Gaussian distribution. When the variance is unknown, sample mean follows a standardized sample mean follows a t distribution. So, in general the statistic is calculated as a t value rather than z value, but when you have large number of observations, then it does not matter, you can always refer to the critical values in the Gaussian distribution. Anyway, so the significance scores are given, and as you scroll down you are given some more pieces of information. For example, you are given the residual standard error. What is this? What do you think this is? Remember that we are working with not yk, but we are working with measured yk, which is y plus ek of a certain variance. Of course, we assume it to be 0 mean, right. Ek has a certain variance sigma square e, which I do not know. What is the variance that we had used? So, this is residual standard error, which is 0.3064 on how many degrees of freedom? 196 degrees or 198 degrees of freedom. Now, what is this is what we will learn in the theory, and then you will understand this value. I will tell you shortly what is this residual standard error. Then you have the multiple r squared. This multiple r squared essentially is your r square extended to the case of multiple regressors. Here we have 2, in fact if you exclude the intercept term, you have 2 regressors. If you have a single regressor, then you talk of r square. Again, it is a measure of how good you have the model has, how well the model has explained the data, and adjusted r square is basically adjustment for the number of parameters. In this case they are pretty close because we have not over parameterized. And finally, you have, of course, the adjusted r square tells you that you have achieved an extremely good fit, and we have managed to do that because the noise levels are low and we have included the correct number of regressors. Finally, you have this F statistic. This F statistic is another way of performing this significance test. Earlier we did this significance test using the t statistic, that is by directly looking at the parameters. We can also conduct this significance test or this kind of hypothesis test by asking how much variance, whether the variance explained by the regressors is more or less or is identical to the variance that is due to the randomness in the data. So, remember we did this earlier, yesterday we wrote this expression, sum square total is sum square predicted plus sum square error when you are using a least squares method. So, what we are doing here is we are asking if the regressors are just explaining the data by chance, and if they are doing that, then both these values should be theoretically identical, because if these regressors I am sorry, this is not for 1. So, you are writing here ymk as y hat plus epsilon k. So, sum square prediction is coming due to is the contribution due to y hat, and sum square error is a contribution due to a prediction error. The simple logic is that if the model, if the regressors that I have included should not have been included, then the variation explained by the regressors should be more or less the same as a variation due to the errors, because they are just explaining by chance, but and otherwise there is no systematic relationship. F statistic is a measure of the ratio of the variance explained by your model to the variance that has gone unexplained. If none of these regressors should have been included, ideally that ratio should be 1, all right, because if there is no, suppose you were to fit a model directly onto some noise and you have included these regressors. Try this out. When you go back, simply generate noise and regress noise onto your kvec square and kvec and see what the results tell you. It will tell you that you should not have included those. In fact, if you are confused, let me just show that. So, you have here, let us say some lin mod 2, we can say just generate some noise here, or we will take the specific noise that we have ykm minus yk. Being regressed on kvec square plus kvec. So, what are we doing here? We are just regressing noise onto these regressors here. It is obviously it is a worthless business, but so there is some purpose to it, in at least in terms of learning. Oops, sorry. So, what do you see here, right? I mean kvec square just explains by chance, but if you look at the estimates and you look at the standard errors and so on, it says your intercept term should not be in the model. The regressor kvec is not significant because there is no star associated with it, that should not be in your model. There is one star, but that is, if you look at the legend here, that is for, you have here the legend for 95%. So, you have 0 is triple star, double star is for 0.001 and so on, but all of them should work out correctly in your favor. In the sense, if you go to the F statistic, if you look at the adjusted R square, how much has these regressors managed to explain? Pretty much, insignificant. That is telling you that these regressors have no role to play in explaining the noise. This is what would happen if you have included a completely wrong set of regressors for your model. And the F statistic also says here, if you look at the p value associated with this F statistic, it essentially tells you that you have not explained anything in the in your series. In this case, it is pure noise with the help of your regressors. So, what I am trying to show you here is how to read the output of a linear regression. You have to look at the estimates, you have to look at the adjusted R square, you have to look at the F statistic and be convinced that the regressors are significant. Now, let us turn to overfitting very quickly and see what kind of parameter estimates do we get when we end up overfitting. So, for this purpose, let us go back to our original model here and now include quadratic a power of 4 terms as well. And let us call this as maybe 4, the 4th order. All right. So, what do you expect to see now as far as the parameter estimates are concerned? The estimates corresponding to the 4th and 3rd order should turn out to be insignificant. Is that the case? We will see. the adjusted R square is still high because you still have included the right number of regressors, but the only point is you have over included the regressors here. Now, let us go and see. So, now what has happened now? Everything has gone for a toss except the intercept term. All the estimates have taken a beating, right. You see that? So, what overfitting does is not necessarily only bring you large errors for the excess regressors, but can also spoil the game for the other important regressors as well. That is why one should try and avoid overfitting, and the traditional approach is a bottoms up approach. What we mean by bottoms up approach is you start with the simple model when in doubt, when you have no prior information, start off with a simple model based on your visual inspection. Here the visual inspection suggests a quadratic, that is why we started off with a quadratic. If that was also not clear, we would have begun with a linear one. Sometimes it can happen that overfitting will show large errors for parameter estimates corresponding to unnecessary regressors, but there is no guarantee. What is definitely known is overfitting will bring in large errors in your parameter estimates. Whether it is for all estimates or part of the estimate set, that depends on the problem entirely. So, for example, here if we were to go back and throw out the fourth order term here, right. So, suppose we do this and now ask for the parameter estimates. Still, of course, adjusted R square remains very high, the model has done a good job of explaining it. But now you see it says that the intercept term, of course, is significant, that is okay. It also says that the coefficients corresponding to k square and k1 are significant, but the coefficient corresponding to k cube is not significant. In this case, it has correctly told me that the excess regressor that I have included should be thrown out. Now, the modeling is completed only when you go back and finish your throw out this additional regressor that you have included and develop your model with the right number of the right kind of regressors. In other words, you can't actually just report. The previous thing showed us, right. The previous thing shows us that you can't say, well, I do not know what is the order of the polynomial, I am going to fit some 50th order polynomial. It should automatically tell me which regressors should be thrown out by telling me the corresponding insignificant parameter estimates. Unfortunately, that does not happen. It can happen that as you see here that it says all parameter estimates are insignificant. Then you have to backtrack and back off and then say, no, maybe I over included, so let me cut down, but that is a problem with a top down approach. Whereas with a bottoms up approach, you are systematically adding. Now, this is a traditional approach which has lasted for several decades, at least for about 60, 70, 80 years you can say. Now, today there are methods which will automatically pick the regressors for you under some conditions, not all times, but not so restrictive. Even if you over parameterize, there are methods which solve a different kind of optimization problem. They do not solve the least squares optimization problem. They solve what is known as a one norm optimization, and there is a method called Lasso, which stands for least absolute shrinkage selection operator. It was developed in mid 90s by people at Stanford, and that essentially selects the right variables for you. You may include some 100 variables in your regressor set, and it will come out and tell you, well, only these regressors should have been included, the other ones should not be included. Of course, provided some conditions are satisfied, we will not go into that. Now, here of course, we are not talking of time series models. When we go to time series models, things become a bit more complicated, but the basic concepts still prevail. So, now you have seen that there are a number of calculations that are being made. For example, sorry, the standard errors are being calculated, then the adjusted R square we had given the expression, but then there is a sum square residual standard error that is being calculated, right, and then I have also talked about distribution and so on. So, let us turn to theory and ask how these calculations are made, and then we will come back to an example on time series modeling, where I will demonstrate to you what kind of biases can result in time series modeling or otherwise. That means you can have unbiased estimates as well, whether we get consistent estimates and so on, in particular with autoregressive models. The reason for confining ourselves to autoregressive models when it comes to ordinary least squares is we are discussing until now the linear least squares. What is linear here? The predictor or the y hat is linear in the unknowns. And AR models, if you recall, they generate predictors that are linear in the parameters, whereas moving average models produce predictors that are non-linear in parameters. So, we are not in a position to apply least squares to estimating moving average models as of now, because in a moving average model the predictor is a non-linear function of theta. Only when we discuss non-linear least squares we will be in a position to talk about moving average models.